Hello, this is Ms. Stevens. Today we're going to look at an easy way to compute the actual area from a scale drawing and knowing its area. All right, so we're going to do 3 examples and then hopefully you'll discover the really easy way to do that. And so we're going to start with just going through these pictures, and we want to know what the scale factor is if you go from the actual picture to the scale drawing. So if I go from 4 units to 8 units, I have to multiply it by 2. So that is going to be scale factor of 2, and I can check it. 2 times 3 is 6, so yes, the scale factor is 2. All right, so then if we look at the actual area of this picture down here, it's 4 units by 3 units. Well, we know that you calculate area. 4 units times 3 units will equal 12 units squared. So make sure you're writing this down. So 12 units squared goes in that blank. And then the scale drawing area, well, we'll look at this area, the bigger one, and we'll say 8 units times 6 units. And that's going to be equal to 48 units squared, or square units, where the little square, this is just the symbol for units. And then if we're doing units times units, units squared, that's where that comes from, that number 2, that's why it's called squared. Okay, the value of the ratio of the scale drawing area to the actual area. Okay, so for that one, we've got the scale drawing area is 48 units squared, and the actual area is 12 units squared. So we can put that little colon in there for ratio. That's the same as the word 2. And whenever we see a ratio written like this, we always know we're going to write it 48 over 12. The first number always goes in the numerator, second in the denominator. And that can be reduced. So if we could just divide 48 by 12, because that's what this fraction bar means. It goes in perfectly. And so the actual area, the ratio of the scale drawing to the actual area is 4. Alrighty, so now let's move on to the next one, the scale factor. If we go from 6 units to 2 units, we're actually dividing 6 by 3. That's the same thing as taking a third. So a third of 6 is 2, a third of 9 is 3. So our scale factor is 1/3. Our actual area, well, again, we're going to take 6 units times 9 units, and that counts up all the squares inside there. That means there's 54 little squares, and we're calling them unit squares. Units times units, units squared. This is a little square. Scale drawing area, 2 units times 3 units is equal to 6 units squared. So the value of the ratio of the scale drawing to the actual area, the scale drawing is 6 units squared, and to the scale drawing to the actual area is 54. So that's going to be 6 to 54, and I can divide out, what would be my common factor? I could divide out a 6 out of both of those. So that's going to be 1/9. So there's my ratio of scale drawing area to actual area. Now the third one, the scale factor, well, this one's a little tougher because my scale factor, well, I know I could multiply it by some k, like I did up here. K was 1/3. Up here, k was 2. So we got to find out what k is here, and that might be a little tougher for you, but all you really have to do is set up a little equation, and I'll just do it right up here. 6 times k has to equal 8. So to get k alone, I can divide both sides by 6, divide out, and they give me 1k, or k alone. So it's going to be 8/6, but I can reduce that. I can divide out a 2 over 2, and so that's going to be 4/3. So if I take 4/3 times 6, I will get 8. And if you don't believe me, try it on your own. So the scale factor is 4/3, and also 4/3 times 9 should give me 12. Okay, so the actual area, ooh, they're triangles. So and we're going to let you use your reference sheet for these problems when you need, and you would have to know the area of a triangle, which you learned last year, and the area of a triangle is going to be 1/2 the base times the height. So we're going to take 1/2, and the base is 6 for this first one, units, and the height is 9 units. So I'm going to go ahead and take 1/2 of 6 first. So 1/2 of 6 is 3 units times 9 units is 27 units squared. Do the same thing for the scale drawing. That'll be 1/2 times 12 units times 8 units. And 1/2 of 12 is 6. And then units and 8 units. So that's going to be 48 units squared. So the value of the ratio of those two drawings is going to be 48, because we're doing scale drawing area. You always make sure you read that. 48 to actual area, which is going to be 27. So 48 over 27, we could divide out a 3. And divide out a 3 in the denominator. So when I divide that out, I'm going to get 16. 48 divided by 3 is 16 ninths. 27 divided by 3. Okay, so now we've got some questions for you to look at. And whoever the sub is, if you would like to pause and let them look at these questions, and then we're going to come back and compare them. All right, welcome back. And it says, what do you notice about the ratio of the areas in examples 1 through 3? Complete the statements below. So it says, when the scale factor of the sides was 2, then the value of the ratio of the area was. Okay, so if we look back, when it was 2, the value of the area was, the value of the ratio of the areas was 4. And you can go back and look at each picture. I'm just going to fill in here. Okay, when the scale factor of the sides was 1/3, then the value of the ratio of the areas was 1/9. And for the last one, it was 4/3. And so the value of the ratio of the area was 16 ninths. And it says, based on these observations, what conclusion can you draw about the scale factor and area? Well, if we go from the scale factor to the area on each of these, when we do area, remember it's in units squared, so we're going to 2 dimensions, so we have a bunch of squares. Well, if we're going from the side length, that's in 1 dimension, so we're going from 1 dimension because you're just measuring the sides, and we multiplied all the sides by 2 to get the new lengths of sides. So if we square this, we get 4. If we square the scale factor that was linear, that was just the lengths of the sides, if we square that scale factor, we get 1/9, because 1/9 times 1/9, 1/3 times 1/3 is 1/9. Up here, 2 times 2 is 4. So down here, if I square 4/3, the same thing should hold true. 4/3, 4 times 4 is 16. 3 squared, 3 times 3 is 9. So our observation then is the ratio of the areas. The ratio of the areas is the scale factor multiplied by itself, or the scale factor is squared. That's just another name for saying take that scale factor times itself. The scale factor of the sides is r. And here we're just saying we could put in any number for r. Okay, we had 3 different pictures. We had 3 different side lengths. So this is just a general way to say it. We could plug or substitute in anything. So if we have that, then the ratio of the areas is going to be, you're going to square that scale factor. So that would be r squared. All right, so our first example, we've got, all right, so it says the student government, the student government, like your half-court basketball plan, they have asked you to calculate the actual area of the court so that they can estimate the cost of the project. All right, so here's an application where we don't have to go back and do a bunch of conversions. We can just use the the ratio of the areas and see what we could use there to actually just convert from one area to the next. And that's what the whole title of this was about. Okay, so based on your drawing, all right, so when we look at our drawing, we've got 1 2/3 inches by 2 inches. And we know from yesterday that if we took 1 2/3 inches and we multiplied it times the scale factor, which was 1 inch to 15 inches, no, 1 inch to 15 feet, I'm sorry. Then if we multiply that scale factor, which is 15 over 1, which we can just say is 15, then that's going to be 1 times 3 is 3, plus 2 is 5/3, times 15 over 1. I can divide out a common factor of 3. So when I multiply straight across, I get 15 over 1, or 15 feet. Oh, I did something wrong there. Oh, divide 3 into 5, and I get, or 15, and I get 5. Thank you. So that's 25 feet. And then down here, this one's easy. So remember our y equals kx. This is like my k here, and this is like my x here. And so this is like my y. So I'm doing k times x, and then I'm getting 25 feet. So the new side length depends on the side length of the actual drawing. And here's the actual side length. So again, I'm doing y equals kx again, and my k again is 15 down here. And this is just, I'm just reviewing what we've done before. And if I take, this is my x, and if I multiply it times 15 feet per inch, then that's going to be 30 feet. And that's my y. All right, so now it says, based on your drawing below, what is the area of the planned what would it be? Well, you would say, well, I've converted these, so now my area is going to be 25 feet times 30 feet, and that's going to equal 750 feet squared. Okay, but to save a step so that we don't have to do all those conversions, what we could do is just find the ratio of the areas. Okay, well, we already know, so if we, okay, let's do, first of all, ratio of areas. That's what we just figured out up in the first 3 examples. So the ratio of areas, we know that if we have a scale factor of 15, and it was 1 inch to 15 feet on the scale, then all we have to do is take the 15 and square it. And when you square that, you can do it on your calculator, you get 225. So this is going to be my ratio of the drawing to the actual. Okay, so I have my ratio of areas is 225. That's the ratio, or this is the scale factor of the sides, but this is the scale ratio of the areas. We had to square it because to get area, you square. All right, so we're going to say that that is my K now. All right, and we know that the scale drawing was 2 inches by 1 2/3 inches, and we knew that that area, if I took 2 inches times 1 2/3 inches, that's going to be the same thing as 2 inches times 3 plus 2 is 5/3 inches. And when I multiply straight across, I have 10/3 inches squared. Now we're going to assume that we already knew that. I just wanted to show you how to get that. So this is the scale drawing area, and there's the scale drawing area. Now if we want the actual area of the picture, or I'm sorry, of the court, okay, so now we can say that the actual area, I'll move over here, got a little more room, so actual area, that we're going to call that y. And that is going to be equal to K times X. And our X is our scale drawing area, which was 10/3. And our ratio of the areas is 225, and that will give me the actual area. So I can put 225 over 1, divide out of 3, and I get 75. And then 75 times 10, that's going to equal 750 feet squared, which is what I got up here. Now you probably say, well, Miss Stevens, this was easier. Here I had to do 2 conversions, okay? Now this was an easy conversion, but if I don't want to have to do those 2 steps, then if I know this, and I know we had to do that step, but normally you won't have to, all right? And this is the scale drawing area. Then all I have to do is this little problem right here and say I'm going to take my ratio of the areas times my old area, or the area of the scale drawing. Then when I multiply those, I get the new area. So this is just a little clean calculation, as opposed to have to convert this, then multiply them together. This was an easy one, but they'll get harder. So I want you to stop here and the sub, and you're going to let them do the problems. There's another handout, and it's actually computing areas where they've got, or I'm sorry, 2 problems, and just pause it and let them do that second handout with the 2 problems on it, and then we'll come back and I will give you the answers to those.